Hello everyone, welcome to lecture 46 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on active hyperbolic metamaterials for various spectral bands. So here is the lecture outline. We will look into active hyperbolic metamaterials for visible and near infrared spectral band. We will discuss about chalcogenide phase change material based active metamaterials, and then we will move on to discussing active hyperbolic metamaterials for mid infrared and terahertz spectral bands. There we will discuss about graphene based active metamaterials. HMMs are hyperbolic metamaterials, right? Topological insulator based active HMMs and superconductor based active HMMs. So let us first look into this topic, that is active HMMs for visible to near infrared spectral band. So the tunability in the visible and near infrared range is crucial for many advanced optical applications, right? So what are the approaches in using active materials? You can think of using liquid crystals, okay? So you can use nanosphere dispersed liquid crystals, that kind of HMMs for NIR tunability. So in this, the external electric field can change the orientation of the liquid crystals, and that will change its optical property. So it alters the effective permittivity and also the dispersion relation, and it enables tuning of the reflection or refraction from normal to negative under TM polarized light. Now you can use liquid crystal plus silver nanowire HMMs for visible wavelengths. So they typically show a tunable dispersion range between 454 to 475 nanometer, and the limitation here is that you get this modest spectral tunability mainly coming from the small refractive index contrast. You can calculate the change in the refractive index, that is delta n, as Ne minus No. E is the extraordinary axis, O will be the ordinary axis, right? The other approach of making active metamaterials is to use phase change materials such as vanadium oxide, okay, or VO2. So VO2 basically shows the transition from metal to insulator phase at 68 degrees centigrade. So its volatile phase behavior can make it attractive for NIR tunability, okay. So you can stack VO2 and TiO2 multi-layers, and by using this metal insulator phase transition in VO2, the dispersion can be tuned from elliptic to hyperbolic dispersion, right. So that is how you can obtain active tunability. Next we will look into chalcogenide phase change materials based active HMMs. So if you compare them with the previous two cases, that is liquid crystal and VO2 based, okay, this kind of phase change materials basically retain their structural phase after switching. So in that case, you need energy only during the switching phase, not for retaining that phase. So you do not need energy continuously. That means this kind of mechanism is much more energy efficient, right. So an ideal phase change material is germanium antimony telluride. It is also called GST or GST 225. This can show significant optical contrast change when it is changed from amorphous to crystalline state, okay, and it can switch in sub nanosecond scale, that is it can go for billions of cycles, right. So you can see the optical behavior in this figure 1, where the optical constants of this GST in the two phases amorphous and crystalline are plotted. So here you see N amorphous, K amorphous, and N crystalline and K crystalline. So it tells you that the contrast in the infrared region is very large between the two, okay. So this solid lines tells you about the N, that is the real part of the refractive index, and the dashed lines basically tell you about K, that is the absorption coefficient or the imaginary part of the refractive index, right. So, first observation is that the contrast is large at near infrared range. Okay. Second observation is that the optical loss is very minimal for wavelength greater than 1500, right. And the key advantage here is that the optical constants of this kind of PCMs can be thermally, optically and electrically activated for rapid tuning. Now, what are the applications of this kind of chalcogenide phase change materials based active hyperbolic metamaterial? So, the applications involve photonic data storage and reconfigurable photonic devices working in the visible and near infrared range. So, the limitation here is that in the visible range this GST material is a lossy dielectric with low index contrast, as you can see here. Okay. However, if you look into the NI region, it gives you pretty good contrast between the two phases, and it can be used for tunable devices, particularly in this range of infrared, but you can also see that they are not very effective in the visible. Now, this particular figure shows you how you can use a GST in a active HMM, hyperbolic metamaterial, for NIR tunability. So, here you consider a multi-layer HMM that is made of GST, silver and germanium. Okay, the thicknesses are written. So, this is basically a multi-layer stack. Okay, and what happens in this case is that here different layers of this material are considered. Okay. So, here you can see in the amorphous phase of GST, okay, it basically the overall structure, which is a multi-layer of this particular stack, is behaving like a hyperbolic metamaterials, okay, and that is showing you negative refraction. However, if you do thermal annealing, that will give you non-volatile phase change of this material. So, your GST will go into the crystalline phase. In that case, it will basically support a regular kind of refraction. So, it is basically tuning from hyperbolic dispersion to a elliptical dispersion in the near infrared regime. So, here you can clearly see that the structure is basically comprised of 7 periods of this kind of multi-layer unit cell stack, you can say. So, let us look into the dispersion behavior, which is clearly shown here. Okay. So, this is the real part of the effective dielectric constant, okay, and this is the wavelength scale. So, you can see that this supports, so this is the real part, okay, of the parallel permittivity, this is the real part of the perpendicular permittivity. Okay. So, this for the amorphous phase and this for the crystalline phase, right. So, you can see that the wavelength starts from 400 to 1200. So, in the case of amorphous, it supports a hyperbolic dispersion over the entire range of 400 to 1200. However, in the case of crystalline, it alters the dispersion into elliptical. Okay. So, when you move into NIR range, okay, before that it is behaving like that hyperbolic dispersion, but then here there is a transition in the crystalline phase, right. So, you can clearly see the TM polarization effect here. So, when the phase switches from amorphous to crystalline, it basically reverses the sign of the Poynting vector, which is parallel to the interface. So, this particular figure shows you both the electric field amplitude, that the background red and blue you are seeing. Okay, that is the electric field amplitude, and the direction of the power flow is shown through these arrows, yellow arrows. So, you can see here that this is your HMM layer, this is air and this is substrate. So, in the first case, when it is amorphous, it is behaving like that type 1 hyperbolic metamaterial. So, you have the Poynting vector where the component parallel to the interface is basically in the left direction. But when it transitions to the crystalline phase, there that component basically changes sign and it is on the right, towards the right direction. Okay. So, that is the change that is happening from negative refraction to positive refraction. Okay. So, that way Many of the GST tunable structures can be used for tunability. However, there is a limitation. So, interdiffusion issues between noble metal like gold, silver and this kind of chalcogenide phase change material like GST comes in this kind of a structure where the noble metals are basically in direct contact with the chalcogenides. So, they can compromise on the device stability and the performance. Okay. So, this interdiffusion basically refers to the mutual diffusion of atoms across the interface of two different materials when they are in contact, especially when subjected to elevated temperatures like during phase change cycles in this kind of phase change materials. So, usually at high temperature during the amorphous crystalline switching of the material like GST, gold and silver atoms, whichever you are using, in this case it was silver, they can basically diffuse into the GST layer, and the tellurium or the other atoms from GST can also diffuse into the metal. So, this basically forms intermetallic compounds like gold, telluride, and they may disrupt the optical property and the phase change functionality of this kind of material. So, now we will also see low loss tunable hyperbolic metamaterial design for visible wavelength, but this time we will be using another material which is antimony trisulfide Sb2S3 with titanium nitride. Okay. So, why we have to go for this? Because we have understood that there are some problems with the existing materials. First of all, GST is basically lossy in the visible range that you can see from this graph also if you go back and look. So, GST is basically lossy here, you have very high K component in the visible range. Okay. Next, we have also seen that when you use noble metal like gold or silver, they cause a strong energy dissipation at the visible range. Okay. And also there are issues with this interdiffusion. Okay, when you put PCM materials, phase change material like GST close to noble materials like gold and silver. Now, how do you overcome these problems? First, you have to go for a low loss material selection. Okay, so you can also look for titanium nitride, which is basically a alternative plasmonic material that will try to help counter that effect of diffusion problem coming from the noble material. And the overall loss is also less. You can see if you use antimony trisulfide, the K values are much lower in this case. So, that will give you a low loss tunable solution if you make a HMM from this kind of material, antimony trisulfide and titanium nitride. So, these are the material advantages. As I mentioned, say antimony trisulfide is a phase change material, but with low optical loss. That is a good thing. It has got a band gap of 2 electron volt, making it transmissive in the visible spectrum. So, it does not absorb the visible light. So, it shows substantial dielectric function changes when you switch from amorphous to crystalline. And on the other hand, titanium nitride, as I already mentioned, it is an alternative plasmonic material that can avoid the diffusion issues that is coming from the noble metal. So, the phase change or the phase switching process, you can think of that your antimony trisulfide is initially in amorphous phase, and when you try to switch to crystalline phase, you have to first anneal the sample at 300 degrees centigrade for 30 minutes and conduct annealing in low pressure argon, since crystallization temperature is typically more than 285 degrees centigrade. So, how do you make this HMM hyperbolic metamaterial? It will consist of 10 layers, alternating layers of antimony trisulfide and titanium nitride on a glass substrate. And this design typically shows sharp non-diffused interfaces between the two materials, and you can use effective medium theory to compute the effective permittivity components, which you can also see over here, right. So, these are the real part of the permittivity. So, the solid lines tells you about the amorphous phase, that is red one is showing, this two basically showing epsilon z, and this two showing you epsilon x and epsilon y. Okay. So that the solid lines are amorphous and the dashed lines are crystalline. So if you mark this axis, so this is 0. So below this here you can see that it is showing the hyperbolic region, right. So the amorphous, so this is basically the amorphous, yeah, there is a small region here also. Okay. If you look into the graph carefully, you can see that the amorphous HMM basically shows a type 1 hyperbolic dispersion for wavelength greater than 580 nanometer, right. And the crystalline HMM, which is shown using the dashed lines, basically shift the hyperbolic band slightly blueward at 564 nanometer. Okay. And this is basically caused by a reduction in the effective index because of the crystallization process. Okay. So that gives us a good idea that what kind of material we will be able to use for those spectral bands. Now we will move on to the next discussion of active hyperbolic metamaterials working in mid-infrared and terahertz spectral bands. So let us first look into a graphene based active hyperbolic metamaterials. So you all know graphene is a plasmonic material effective in mid-infrared and terahertz frequencies. So here is a multi-layer graphene based HMM structure. So you have got 2D graphene sheets which are separated by dielectric spacer, and you can apply external gate voltage to tune the carrier density that basically changes the dispersion from elliptical to hyperbolic. And this tuning mechanism basically modulates the in-plane conductivity, and hence there will be a different optical behavior. You can use graphene based HMMs for negative group index tuning. So you can see the proposed structure which is shown here, which is graphene dielectric multi-layer stack. So for mid-infrared wavelength operation, you can choose alumina or Al2O3 as the dielectric material. The structure that is considered here is basically having 12 alternating layers of graphene and dielectric with graphene on the top. So how do you model this? You can model the single layer graphene as a surface conducting sheet where the conductivity is given by this expression, sigma g given as I e square omega divided by pi h bar square omega plus I by tau. Omega is nothing but the angular frequency. Mu here is something interesting, that is the chemical potential that depends on the carrier density because mu is proportional to square root of Nc, and tau tells you about the electron relaxation time. So once you can estimate this conductivity, you can always get the complex dielectric constant of the graphene given as epsilon g equals 1 plus I sigma g eta naught divided by k naught Tg. So k naught is basically the vacuum wave vector, that is omega by c. Tg is the effective graphene thickness, and eta naught is the free space impedance, that is 377 ohm, right. So with this you can use effective medium theory, and you can estimate the real parts of the effective in-plane permittivity, and here is the plot that is shown versus frequency at different chemical potential, right. So what you can observe, that hyperbolic dispersion basically occurs when you have the real part of the parallel permittivity being negative. So that is here for the case of Td equals 50, and in this particular case it is considered mu equals 0.2. Okay. So this frequency. So you can see the transition basically happens from elliptic to hyperbolic at 24 terahertz, right. And in this particular figure you can also see that how you can tune this hyperbolic spectral band by changing the chemical potential. So when you have the chemical potential mu equals 0.2 electron volt, that transition happens at 24 terahertz, but when you change the chemical potential to 0.8 electron volt, you can change that transition frequency to 49 terahertz. Now this mu is the chemical potential which basically depends on the carrier density, right. So that is where you can actually change the carrier density, okay, in graphene to change its chemical potential, and that will change this transition frequency between elliptical to hyperbolic material dispersion curve, and that will dramatically change its optical response, or you can say the response to that particular wave. Now we will look into another type, which is topological insulator based active metamaterials, hyperbolic metamaterials. So topological insulators we have briefly discussed earlier. They have gained particular interest in this terahertz plasmonics, and they allows you to make this tunable hyperbolic metamaterials. Common type of topological insulators are bismuth selenide, Bi2Se3, and bismuth telluride, which is Bi2Te3. Okay, and they are known for gapless edge or surface states and a bulk insulating properties. So let us consider this one, bismuth selenide, which is basically a quintuple layered, and that has been analyzed for hyperbolic dispersion in the terahertz range, as we have already discussed this in the second application of active hyperbolic metamaterial, that is supercollimation of terahertz light. Now topological insulator based HMMs, they are particularly interesting because they support highly directional subdiffractional hyperbolic phonon polaritons, right. So they have dispersion tunability that is coming from surface state doping, and they enable realization of high speed tunable terahertz photonic devices. So if you carefully look into this particular figure, that is telling you the quintuple structure of this bismuth selenide, which is a topological insulator. So it is basically having those 5 atomic layers which are stacked in a particular sequence. You have Se, Bi, Se, Bi, Se, that is the sequence. Okay. So these quintuple layers are basically the fundamental building blocks of this crystal structure, and they are weakly bonded together by van der Waals attraction. So this is basically repeated, right. And this particular topological insulator, why it is particularly interesting, because you can make dynamically tunable terahertz photonic devices using this kind of materials. So here we will take one example, but we take the example of the other one this time, the other topological insulator material, that is the bismuth telluride, and we take germanium telluride GET as a phase change material, and we make their alternating layers, okay, to form this multi-layer structure that will work as hyperbolic metamaterials. So these are the alternating layers of these two materials. So why we use this? Because this particular material, bismuth telluride, is structurally similar to bismuth selenide, and we use germanium telluride as a phase change material here. And you will see that the negative group index band can be tuned from terahertz to mid infrared frequencies in this particular case. So again, you can use effective medium theory for modeling the permittivities. So you can first consider the dielectric permittivity of this bismuth telluride. It can be obtained using a Drude-Lorentz model. We have discussed this earlier. So you can use this particular model, epsilon omega equals epsilon infinity minus omega d square divided by omega square plus I omega d. Okay, so this is basically the Drude term, and then you have the Lorentz oscillator model. So you have summation over j equals 1 to how many Lorentz oscillators you are be using. Then you have omega p square j divided by omega naught square j minus omega square minus I omega gamma j, right. So here epsilon infinity is basically the high frequency permittivity, epsilon d is the Drude plasma frequency, gamma d is the damping rate, okay, and these are the plasma frequency, resonance frequency, and the damping coefficient for jth oscillator. Okay. So with that you can model bismuth telluride. For the case of germanium telluride, you can see that the amorphous phase has a dielectric permittivity of 15 at terahertz frequency. Okay. So if you consider this bismuth telluride or the topological insulator to have a filling fraction of 35% or 0.35. So, this structure can actually give you a HMM kind of structure, which will exhibit a broadband type 2 hyperbolic dispersion from terahertz to mid infrared frequencies, which you can also see here. So, this is considering germanium telluride in the amorphous phase. So, here you obtain epsilon x to be negative and epsilon z to be positive. Okay. For the germanium telluride in crystalline phase, the permittivities are plotted here. So, here you see that when you have crystalline phase, the HMM will display both type 1 and type 2 hyperbolic bands, and that is very unique property. Okay. So, what are the applications? This kind of tunable optical properties are basically achieved from the phase change of germanium telluride. So, it is basically changing from amorphous to crystalline, and also from if you dope this bismuth telluride surface states, okay, you can get tunable optical properties, and that can be used for different applications. Next, we will look into superconductor based active hyperbolic metamaterials. So, in this case, high critical temperature superconductors or HTS, they also can enable hyperbolic dispersion in the infrared and terahertz frequencies. So, superconductivity here occurs above liquid nitrogen temperature, making them practical in regular operations. So, superconductor based HMMs can also help raise the critical temperature that offers metamaterial based approach for high critical temperature superconductivity. So, the proposed structure basically comprises of multi-layer of YBCO, that is yttrium barium copper oxide, and LAO, that is lanthanum aluminate. Okay. Now, why you choose these two material? So, YBCO is basically a common high critical temperature superconductor, and LAO, lanthanum aluminate, is a dielectric that basically supports lattice matched deposition of these YBCO films. So, that becomes a natural choice. Now, what are the material properties? The material properties are LAO permittivity is around 25. Okay. So, here you can see that these are the effective medium theory derived permittivity components. The A tells you about the real part and B tells you about the imaginary part at different temperatures. Okay. So, this is for the overall material, but in doing this calculation, you also need to take care of the constituent material permittivity. So, here LAO permittivity is considered to be around 25 and it is temperature independent. So, it is flat. Okay. And then if you consider YBCO permittivity, that varies significantly with temperature and frequency, right. So, this particular figure shows the real and imaginary part of the parallel. So, this actually epsilon parallel and perpendicular being plotted. So, this is the perpendicular one, this is the parallel one, and this is the imaginary of the parallel and imaginary of the perpendicular components. Okay. So, the temperature range considered here is from 20 K to 100 K, because that is particularly interesting, because YBCO's superconducting transition temperature is within this 80 to 93 K. Okay. So, above 100 K, that is above your critical temperature, you will see that both real and imaginary permittivities are positive. That basically indicates elliptical or dielectric dispersion curve. Now, what happens below this transition temperature? You will see that the real part of the epsilon parallel becoming negative, that signals type 2 kind of hyperbolic dispersion, and it is also clear that the hyperbolic dispersion bandwidth increases as the temperature decreases. And this is mainly due to the increasing frequency dependent conductivity of this yttrium barium copper oxide. It is due to the increasing frequency dependent conductivity of YBCO in the superconducting state. Okay. So, and this finally demonstrates that you have a temperature driven transition from elliptical, that is a dielectric, to hyperbolic kind of dispersion, and you can have broadband tunability as seen here for hyperbolic response that is coming from temperature change, right. So, with that we will conclude our discussion. So, in the next we will talk about metamaterials for electromagnetic cloaking. So, if you have any query regarding this lecture, you can drop an email to this email address mentioning the lecture number and the course name in the subject line. Thank you.